Okay, so at some point I'll have to erase all of these functions. So either copy it down or commit it to memory. I think copying it down might be easier. Nonetheless, I had defined 4 functions, u plus, v plus, phi plus, I should say theta plus, but theta plus is the same as theta. And it's defined in terms of the star coordinate and the bar coordinate. And you will also find a constant kappa. All we have used here is kappa plus, but I've stated kappa plus and kappa minus. The minus, of course, is for future use. And when we start using the minus, all of these u plus, v plus will become u minus, v minus, phi minus, and so on and so forth. But generally what we do is the same. I've also shown that this is well defined on block 1 and block 2, including r equals r plus. Remember, the blocks don't include the horizon. In particular, this is defined because u plus in both 1 and 2 takes this form. So when r equals r plus, it's just 0. So it smoothly connects. So although blocks 1 and 2 don't include r plus, these coordinates can be extended to r equals. So I should say defined on r bar equals r plus. We have shown this. So very quickly, and I want to get to the more geometric part where I'm literally drawing pictures, because really most of our hard work is over. But there are interesting features about time orientation that I want to sort of clarify. But the first thing is, very quickly, I want to show that u plus, v plus, theta plus, phi plus defines a coordinate system on r bar greater than r minus. Too many bars and minuses, but we know what they mean. I really shouldn't say r bar. It is r bar equals r, but so all we're really doing is including, as I mentioned, so it's not sufficient. We have shown that's well defined and it's continuous along r plus. All we have to show is that the Jacobian does not vanish. So it's a very simple proof. These are all computations. If you take these definitions, you'll very quickly see this. There's nothing mysterious about this. dv plus, d u plus, and d phi plus is given by the matrix. Theta is not affected by anything else. You may not see the fine print, so as I write it down, I'm going to read it. This is just the Jacobian matrix, 1, 0, 0, 0, 0, kappa plus v plus 0, 0. This is 0, partial with respect to t bar of u plus, and partial with respect to r bar of u plus 0. This is 0 minus a over r plus squared plus a squared. 0 minus a, this is the second entry, minus a over r plus squared plus a squared, minus a prime. I'll explain what that is. This is the expression we've seen before. Let me write it, and then I'll read it out. Okay, hold on. 0, 0, 0, 1, and I've left a gap here. let me d. This is t prime. D theta bar, dt bar. We'll see very quickly where this comes from. Something mysterious about this. Okay, that's that. And by this, it's just dA, dr, and t prime. Okay, well, d theta prime is not affected by anything else, so it's clearly 1. Look at dv. It is only a function of t bar. And when you take a derivative, so this is dv plus, and this is dt bar. So the Jacobian matrix is the time derivative of that, so kappa plus comes out, because it's the derivative of the exponential. And so u is a function in bar coordinates of t bar and r bar. So it's t bar here for that, r bar over here for dr coefficient, and 0. And this thing just carry it through. This is the Jacobian. And the determinant of this guy, determinant of this matrix right here is equal to kappa plus v plus du plus dr bar. So let me just read it. Kappa plus v plus du plus dr bar. On the horizon or anywhere else finite, v plus is not 0 because it's simply t bar. So this Jacobian is not 0 as long as du plus dr bar is not 0. As a matter of fact, it is greater than 0. I'll give you a couple of steps. Normally, I would assign it as homework. You can just verify. After all, there's this expression right here. But so I'll write 2 steps. All I'll do is show that this is greater than 0. If this is greater than 0, the Jacobian is not 0, so this transformation is well defined and it's smooth. Therefore, this forms a coordinate system. Are we good so far? Yeah. So, using this expression, look, there's this minus t that doesn't suffer any derivatives, so I just bring it to this side. That's why I get this term, so that I don't write it out. And what I get is simply exp to kappa plus r minus r minus r minus r minus. This always has an exponent. R minus R plus 1 times R minus R minus R minus R plus R minus over R plus 2 we really have to verify this is not 0 at the horizon. Everywhere else it's smooth in the first place. This goes to 0 at the horizon, R plus, because between 1 and 2 there's only R plus, there's no R minus. So this whole thing goes to 0, and this is non-zero. So, and therefore it forms a nice coordinate system. I'm really aching to draw a diagram. that'll tell a good bit of the story. We'll have to work a little hard for time orientation. Are we good? So what I'm going to do is I want to draw a diagram. It's one, what kind of a diagram am I wanting to draw? Well, I want to draw something to the effect of, r plus over here, and then, it's a horizon, so something like r plus over here, maybe like you're used to. That's sort of the diagram. If you know the maximal short shield geometry, you've seen these diagrams. You may know of Penrose tiles. That's what I want to do. I want to take this and change this into a diagram. So, to do this, I'm just going to focus on block 1. Block 2 works out similarly. I'm just going to focus on this guy. Block 1 bar. And I also recall that limit r approaches r plus r minus of t of r, because I will have, from here, I will have t of r. This is equal to minus plus infinity. So I'm going to do two things. I'm going to tackle block 1 in the bar coordinate system and in the star coordinate system. And I'm also going to introduce uppercase U plus and V plus by U plus is equal to tangent of uppercase U plus, and V plus is equal to tangent. This is not strictly necessary. The reason I'm doing this is, of course, to somewhat compactify. Not necessarily in a topological sense, it's not compact, but instead of going from 0 to infinity, I can go from 0 to pi over 2. Or from negative infinity to infinity, I can go from negative pi over 2 to pi over 2. So, to make a simple thing complicated, it's always easy to unpack when we complicate it. So I'm going to do block 1 in bar CS. When I do this, gosh, I'm just going to have to erase. I have tangent big U is equal to exp minus kappa plus. I'm writing everything in bar coordinate system because I just said I want to study this in the bar coordinate system. Any conceptual questions before? I mean, the math itself is fairly simple, but any conceptual questions? Okay. Again, law of conservation of space, at least on a blackboard. As r approaches r plus, I've shown there that t approaches minus infinity, which implies, let's see if this is correct, big U, U plus, or I should say approaches 0. Well, that's true. Let's see. This approaches minus infinity, so U plus approaches 0. And 2, as r approaches infinity, t just goes to infinity because t has a direct r dependence in there. So U plus approaches pi over 2. Remember, if you look at t, there's an r term, there's a natural log of r minus r plus term, there's a coefficient here, and I think that's a minus. You could tell. Yeah, this is a plus and this is a minus. this is generally how, and these are all positive coefficients. That is why, in fact, as r approaches r plus, this goes to minus infinity. Okay, so u plus approaches pi over 2 as t bar approaches infinity, v plus approaches pi over 2. Let's see, t bar approaches infinity, v approaches tangent of infinity, and as t bar approaches minus infinity, now I get. So now you might say, wait a minute, over here, and let me use a different color chalk. And the answer is we can say this. Can you say u plus approaches 0? Because let's look at this. T bar approaches infinity. You might say that u plus should go to 0. That you cannot say that, because this has an r dependence, and depending on r approaching r plus or infinity, this too has plus and minus infinity. So you cannot, 0 times infinity is not well defined. So this you cannot say. In fact, it is not true. Similarly, you might want to say here, u plus approaches pi over 2. And the answer to both of these questions is no. It depends on how you go to infinity. So, but these are the clear markings where things happen without question. Yeah? Any questions? So, what I'm going to do is draw my first diagram. I need this space, I need all of this, so might as well write it as necessary. And I'm going to have a horizon in mind. And what I have just written here translates to the following. This is just block 1. Because this analysis was done on block 1, and this is of course pi over 2 and pi over 2, and I have t bar approaches minus infinity, r bar approaches, let me explain, r bar approaches r plus, and t bar approaches infinity. T bar approaches infinity, v plus approaches pi over 2, and as, look at this, r approaches r plus, you get u plus is equal to 0, so along this axis. This is how you would label. As r approaches infinity, u plus approaches pi over 2. So in the block 1 bar, 2 bar, I have just drawn block 1. Any questions? I'll give you a minute to digest.
have to repeat this for how many times?
Infinitely many times. But we will do this. Well, let me show you how non-trivial it is. So let me leave that diagram. This diagram itself is not complete. Let me do block 1 bar in star coordinate system. So just bear with me. Here, tangent u plus is equal to, I leave everything in star, kappa plus t star, and tangent v plus is equal to kappa plus t star. I don't have space here, so times exponent 2 kappa plus t. This t is a function of r. So let me write this down one more time. The limits, we'll check for 1 or 2 very quickly. As r star approaches r plus, v plus is equal to 0. So I get this one. This is minus infinity. So exponent of minus infinity is 0. So v plus is 0 for any finite t bar. As r star approaches infinity, v plus equals pi over 2. V plus. You can check these. These are details, but it's important to check. Nonetheless, there's nothing groundbreaking happening here. Well, actually, I should write approaches 0, approaches pi over 2, approaches 0, and as t star approaches minus infinity, I get u plus approaches pi over 2. So now, when I embed this information to that diagram, I get 4 more labels. And that's absolutely crucial. I should say at this point, equal to, or so this line. Let me replace them with equal to. Either way, it's an abuse of notation, so let's consistently abuse notation. We'll check 1 or 2. Oh, so yeah, remember t bar equals t minus, what is it? T, correct? Or plus? Plus. T star is t minus t. This is the black hole coordinate system. This is the white hole coordinate system. So in this case, n is d r bar. In this case, the outgoing geodesic is, n is minus. So in the bar coordinate system, n is future pointing everywhere because this is well defined everywhere. So its infalling is future pointing. In the star coordinate system, L is that, it's outward pointing, so it's a white hole coordinate system. So look at how these, so for example, you can see as r star approaches r plus, v plus is 0. So if I look at the v-axis and set it equal to 0, I get this. So that's how I have, so there are two things happening here. The bar time runs this way and space runs that way, or this way. But for star, it's the other way around. So you can see, so T star, for example, increases this way. This is just block 1. There's block 2.
And the star coordinates won't cover block 2.
I'm sorry?
The star coordinates won't cover block 2.
You can write it in both coordinate system.
Block 2?
Yeah. I mean, we'll use u plus v plus theta plus phi plus as something that defines the entire region. But if you exclude the horizon, we can use any coordinate system, the star plus or the star or bar coordinate system. But to cross the boundary, we have to use the you are correct. If we call it bar coordinate system, then the bar goes through the horizon as well. But now our anchor on 1 and 2 would be the u plus v plus phi plus theta plus. Okay. So since we started this discussion, let me jot your memory, because I want to see, I'm going to put more of these tiles, but more importantly, I want to know which way is future, which way is past, and more important, and that's the real difficulty, and more importantly, if this is consistent. So the coordinates that I erased here, I want to conclude along n, t bar equals constant. Is that correct? Of course, because n is ddr bar or minus ddr bar. So t bar is constant. So over here, I know which way, eventually I want to draw n and l everywhere. Along L, T star equals constant, because L is T dd R star. In bar, so K bar, when R minus R plus R minus L is future pointing. No, we had discussed this. Otherwise, outward geodesics would be future pointing, and you cannot have that in a black hole system. So it's minus L. So similarly, in the star coordinate system, when R minus R, R plus, minus N is future pointing null. All right, so now what I want to do is see how time coordinate increases or decreases along geodesics. This is a little bit, there's no difficulty, there's no intellectual difficulty. It's just keeping track of things. This is because I want to draw N and L here. So I want to know, for example, I would imagine N would point this way. The question is, which way does L point? Well, in 1, it might be easy. In 2, it may not be so easy. So I want to just do a little bit of math to clean it up. So at the end, I'm going to conclude by drawing a diagram. So how T star changes along N. Well, let's see. T star equals T bar minus 2 TR, because I know how T bar behaves. It's a constant. Therefore, dt star dr bar is equal to minus 2 times the derivative of this. We know what that is. Yeah? So in block 1, D is less than 0. Therefore, as R increases, T star decreases. Correct? As R increases, because this is less than 0, T star decreases. But that's not the point, but N flows along a decrease in R. Therefore, along N, T star decreases. Let me pause here and highlight something and also show you why this big mess. So we know T bar is constant along N. And N falls into the horizon. So this is T bar equals minus infinity, this is T bar equals plus infinity. So T bar has to be constant. So in this diagram, N must point in this direction. Clear? Infalling geodesic points in this direction. But then you go, wait a minute, that's fine. T bar is a constant. Look at the T star coordinate. What is T star doing? Well, I just concluded the opposite of what I wanted. But N flows along a decrease in R, therefore increases. If this decreases, yeah? And that's fine. So do you understand this diagram? Every other diagram will be in our same argument. Yeah. In block 2, the reverse happens. In block 2, delta is negative. We haven't drawn block 2 yet, but these are just collective facts you need. In block 2, along N, T star decreases. All facts that I'll be needing and I'll be erasing. And next, so in block 1, T bar, let me increases along L. Because this is greater than 0, as R increases, this is greater than 0, along L, R increases, therefore T bar increases. And finally, I'm so sorry, in block 2, just facts. If you copy it down, when we draw the diagram, in block 2, wait a minute, in block 2, increases, yeah, dt bar is less than 0, therefore t bar increases along r. However, this is correct. In block 2, dt bar dr is less than 0. Therefore, t bar decreases along r. However, minus L is future pointing null in block 2. Therefore, once again, t bar increases along and that's the future pointing direction. Okay, so what I'm going to do, that seems like a whole lot of trivia. How are we doing on time? 36 minutes? Okay, so I can do a little bit more, and I'm going to do the following and just finally draw a big diagram. Any questions here so far? If I've made a small mistake here, I hope you'll unpack it. I don't think I have, but the argument is the same. The diagram at the end is correct, I think, because it's beautiful. It's one big, beautiful diagram. I'm going to define one bar, 2 bar, 1 bar prime, and in each case I'll define little u, you know what these are, but I'll just write it down for the sake of writing it down. Because you've seen it for 1 and 2, it is. And you're thinking, this is the time we're going to use kappa minus. The answer is no. And here, I'm just going to flip the sign. This is minus, so this will be positive. Fixing coordinate systems do not fix time orientation. Are we losing contact? Do we have sense of the things that I have defined at least? Yeah. And fixing coordinate systems do not fix time orientation. So here is my declaration of time orientation. Block 1. Ln is future pointing null. Block 2 bar n minus L, correct? Is future pointing null. Block 2 bar, it's the flip of this. Minus n and L is future pointing null. And block, it's minus L minus n, which is future pointing null. This is just declared. You can't declare arbitrarily. You have 2 copies of block 1 and 2. On these separate blocks, time orientation has been declared. The question is, if I make a nice patch of all of this, is it continuous? Is it non-vanishing and continuous? And this will be using the recipe of all the hard work. My conclusion today would be just a diagram. If I can draw my axes correctly, we are in business. So I need my axes for this is the uppercase, so that stops at minus pi over 2, pi over 2. So this is pi over 2 minus pi over 2 minus pi over 2 pi over 2. This is my block 1 bar, 2 bar, 2 bar prime, 1 bar prime. Let me write out all the functions. Let me start with the ones, let me write the bar ones, and T bar equals infinity, R bar equals infinity. And I want you to be somewhat in disbelief at this diagram. T bar equals infinity, T bar equals infinity, R bar equals infinity, and R bar equals R minus. Let me write the star labels exactly like we proceeded. We did this in detail for block 1. If you can do it once, you can do it 4 times. And this is T star equals minus infinity, I'll tell you what are some of the problems with this and what are the quick cure. R star equals infinity, T star equals minus infinity, T star equals minus infinity, this is R star equals R minus. I forgot to put one label. T bar equals infinity. And I forgot this one too. R star equals infinity. Okay, the diagram has various other features. Using the bar coordinates, we have now, the dashed lines is not included in the space-time, so I'm going to fix that. We can cross the horizon using the bar coordinates. These guys belong in the space-time. Now notice here, at least time seems to be the same, but these R star coordinates are completely different. So you're going, what kind of a diagram is this? That's okay, this is dashed, it doesn't belong to the space-time. So you'll find always there'll be something that matches, but another coordinate that does not match. Okay? So there's, and you'll find the same feature everywhere. But the horizons have been included. Oh, and I've realized now that I have not written the labels on the horizon. So this is T star equals infinity, R bar equals R plus, and I'm reading it out loud so that if it's not legible, it should be clear to you. T bar equals minus infinity, R star equals R plus, T bar equals minus infinity, R star equals R plus. So look at what's happening now. Did I label everything? Oh, this guy. T star equals infinity, and R bar equals R plus. Now, notice these are solid lines. They belong to our space-time. And look at how they agree. Look at this, and that agrees. Nowhere in our patch at the moment are we able to handle this. We'll easily handle it. We'll just handle it by agreeing to handle it, just saying, well, u equals 0, v equals 0 can be handled. To do that, we'll study the horizons a little carefully. Let me draw one more feature, and then I'll take, I won't be doing anything else, so I'll take any questions that I might have. So let me draw this. I've declared all the future pointings, and thankfully that's here. I'm drawing only the future pointing null vectors. N falls into the horizon, L goes to R star equals infinity. And at this point also you should be asking, what am I drawing? Does that make sense? This is minus L minus N and minus L N. Correct. Let's see, block 1, L and N is future pointing. Let's just do 2 bar. So 2 bar, it's minus N and L. Minus N and L. Block 1 bar, minus L and minus N is future pointing. Now you'll say, well, why did I label it this way? How did I know which way is what? Remember, we had made a tally on which way T increases for L and N. So for example, I have shown that in block, let's say 2, for minus L, that T bar increases. So that's how I know how to point this way. So that way I know in 1 and 2 which way is L and L bar pointing. Now, I have picked this orientation by that declaration, and at least you can see that it looks continuous. We'll do much more than that. We will show that it is in fact continuous. You cannot, and also we'll fill in this hole. So let me take 2-3 minutes out and just answer any questions that you might have.
Do the vector fields not have to be smooth across this boundary?
Which vector fields?
L, for example.
Well, the future pointing is smooth. It's just smooth.
It goes from L to minus L?
Well, yeah, it does. Because minus L is future pointing in 2 bar. L is not future pointing. L will look like this. And so maybe I should also say that in this diagram, this is my light cone. Yeah. Throughout this diagram. You see? This is not intellectually complicated, mathematically complicated, but it's convoluted. If I declare these things to be future pointing, it looks like that. We'll suffer a little bit more, and I'll show you why it is necessary to flip the orientation, and why would that make it continuous. And here too, the nexus of the universe, R plus meets R plus.
So for along U plus equals 0, L and minus L are both future pointing now?
No, that'll never happen. I have to define future on the horizon.
Oh, I see.
Yeah. It'll be continuously defined.
Oh, I see.
Yeah. So
for primed to unprimed,
yeah,
versa, then you need the star coordinates, right?
prime to well, so U and V and theta and phi is well defined all for every block. You just like we tried for this pair, you can, using the star chart, you can fix it for these 2 pair and these 2 pair, and use the bar chart for these 2 pair. Yeah, correct. Now, another thing is, if you look at L over here, this is going to be future complete. L goes all the way to infinity. Now, obviously, we want L to be past complete if it doesn't hit singularity. So unfortunately, we'll have another 4 rectangles so that L could live forever. Same thing over N here. If you look at N here, it is past complete. N has to enter a region 3. So that it can live forever. It either hits the singularity or lives forever. I mean, you can tell it's past complete because of this nice, the minus infinity, or sorry, actually R bar equals infinity. Remember, L is minus d R bar. So when R bar equals minus infinity, it's lived forever in the past. So this is past complete, not future complete. It has to go through. L is future complete here.
So how do you know that it is past complete by looking at the value of the coordinate? Because
I mean, look at, because in the bar coordinate system, so when r approaches infinity, it has already lived a lifetime. The reverse happens for L. So all these, so L is future complete and N is past complete in this diagram. We have to talk about the horizon, and we have to talk about this guy, and we'll include this guy in the UV coordinate system. It is simple, we just include it. And in including it, we will show that on the horizon, these geodesics are already future and past complete. Again, one of the plot of all of this is N and L should be future and past complete unless it runs into a singularity. I've suppressed the theta coordinate system, so there's no way to isolate that. So this is the diagram that we want to remember, and next time I think I'll be able to wrap it up, but I might begin with drawing this diagram. Okay.